Hey guys, what's up? Okay. Well, let's go and get started with today's video, which is graphs. It's going to be looking at position time graph, distance time graph, displacement time graph, velocity time graph, acceleration time graph, blah blah. I'm going to be looking at 3 graphs today. Okay? But if you haven't watched my previous video already, go watch it. Because in the first video I went through an introductory level introduction to acceleration, scalar quantity, vector quantities, velocity, speed, distance, time, everything. Acceleration, kinematic equations, relative velocity, what's reference points, all that. So you don't want to miss out on all that. So go watch it, okay? But today we're going to be doing something fun. We're going to be looking at position graphs. So firstly, what is a position time graph? Let me take this separately. Okay, hope you guys can see it fully. Let me just explain it here. A position time graph, right, is basically a displacement time graph. So suppose on this axis right here, it's the displacement, just so you know. The y-axis is the displacement. So that's the displacement and that's the time on the bottom. Okay? I should probably lower my cursor. Yeah, that's better. So what are the properties of a position time graph? Well, the starting point, right, or the y-intercept of the graph, where it starts, the y-intercept is the starting point of the graph. Okay? So if this is where the position starts, this is where he's starting. Okay? The y-intercept is the starting point. Because it logically makes sense doing math too. When x is equal to 0, you get your y-end. Okay? Then, why is this highlighted? Well, this is the slope, right? Right? So what is the slope in a position time graph? Well, it's velocity. Why? You might be wondering. That's what you always should wonder. Why is that slope the velocity? Well, what's slope? Slope is equal to rise on run, right? What's rise on run? Rise on run is here in our scenario. Rise is displacement. See that? Rise is displacement and run is time. What's displacement over time? Velocity, beta. Displacement over time is velocity. So the slope is the velocity. So this is velocity and that's velocity. What's happening here? As you can read, it's stationary. The object is stationary from what? From 2 seconds to 4 seconds. He's stationary, he's not moving. So in a position time graph, he's stationary. Okay? Now, suppose you want to find something like the distance or you want to find the displacement. You want to add the rise for distance. And you want to compare the start and the end point for displacement. Simple. So for displacement, suppose this is 1, rounded up to 1, right? And it ended at 0. You're just going to displacement is just a straight line down. So the displacement is, you go down 1, negative 1. So displacement for this position time graph example that we have is negative 1 because you're going down just once. Am I right? 1. So you're comparing the start point here to the end point here. Go down. But the distance, for the distance, you add the rise. Okay? So starting from here, this point and this point. Okay, you're adding the rise. You're adding the rise here. You're adding the rise here. Why are we only doing it at 2 points, I think? Because it's only happening at 2 points. Just think. When it's stationary, there is no rise. So the only time rise is happening is from this interval to this distance interval, and from this distance interval to this distance interval. So if we label this something like A, B, C, D, rise is only happening between the C, A intervals, distance intervals, and B, D distance interval. A, B distance interval, nothing, it's stationary, so nothing is happening. Okay? So that's why you want to add the rise to calculate the distance. Okay? You want to add the rise to calculate the distance in a position time graph. Okay? Hope that was clear. I'll erase all this. Oopsie daisy. And that's the position time graph. Now let's look at something like the, velocity time graph to make the most of the sense. Delete, go. Well, rearrange, buddy. Copy. Oh, wait. Okay, now I'll do this one by one. Don't wanna go and organize stuff now. Okay. Velocity time graphs. Look at that. Okay. Now, what is a velocity time graph? Well, as you might have thought about it already, velocity goes on the y-axis and this time goes on the x-axis. That's a velocity time graph. Now, this graph looks crazy. Like, what's happening, man? What's happening? Now, a velocity time graph that's constant, right? Goes by numbers. It goes by lines. So you're not having like, fancy shapes. Because what happens in this fancy shapes, it means it's constantly changing. Okay? So in a constant velocity time graph, it's gonna be like this, and here to here, stuff like that. Okay? It's gonna be horizontal lines. Now, let's see why these horizontal lines work as they're intended to. Okay, so all this horizontal line is saying here is that at what do you call it? A velocity of 1, it's traveling for 3 seconds. So it's that. Then at 2, it's traveling for 2 seconds. At a velocity of 2, it's traveling for 2 seconds. And then at the velocity of -1, it's traveling for 2 seconds again. And it's traveling at a velocity of 0 for, 3 seconds. Right? That's what it's showing. So that's velocity time graph. Yeah, you get the fact. But what makes it special? What are we trying to extract from this graph? Well, usually from a velocity time graph, as you know, what's velocity? It's the rate of change of displacement. So the area under this graph is the displacement. Okay, simple. So in a position time graph, if the axis is a distance, if the axis is x, y is displacement and time, the thing you're finding is velocity. If it's distance and time you're finding is speed. That's the area under the graph. So the area under this graph is total displacement because it's velocity over time, which is displacement. So total displacement, how do you calculate this, you might ask? Well, just multiply the area under the graph. Take the shapes, multiply. See what's the area of a rectangle? Because these are all rectangles, right? It's 3 into 1, which is 1 meter per second into 3 seconds, which is 3 meters, okay, plus 3. Put the directions. So this is what? Plus 2 multiplied by 2 plus 4. Here, well, it's 0. So it's no use, it's going to be 0. Because 0 times anything is 0. And here, it's -1. So -1 times the 2 seconds that you travel, the area under there is -2. So when you add everything up, right, for the total displacement, which is the area under the graph, wait, the area under the graph, it seems confusing because, yeah, sure, the area under the graph is here for that. But for the negative number, isn't the area under the graph going to infinity? No. It's the area under the graph's meaning is the area from the line, horizontal line, to the x-axis. That's what they mean by area under the graph. Okay? So, add everything. What's 3 plus 4? 7 meters minus 2, 5 meters. So total displacement is plus minus 5 meters. Okay? Okay. So now we are able to understand the Vt is equal to velocity, or velocity is equal to Vt. now you know why displacement, right? This is a graphical explanation to why the displacement, which is s vector arrow, because it's a vector quantity, why displacement is equal to the time multiplied by velocity. You've seen it firsthand. That is firsthand. Okay. Now, putting that back, we're going to be looking at this one, this little guy. Copy. Paste. Okay. Let's look at velocity time graph again. But this time, it's not a constant velocity, it's a velocity that's changing. Okay? So it's more fun. Well, I personally like this more because that's just line. Okay, so the red arrow is your line. That's your velocity time graph. That's all they're going to give you in the exam. The highlighted stuff is for me to make it easy for you. Okay? Okay, so let me explain this again. Velocity time graph. What's on the y? Velocity. What's on the x? Displacement. Oh, time. Loses. Okay, so we're going to be calculating the area under the graph for the total displacement, right? Simple. That's all we know. It's the same function except it's changing. And what's the slope? How did I not think of this? What's the slope? Well, the slope is the rise over run. Let's do some. It's the rise over the run. The rise it's time over velocity. It's displacement. If the slope is displacement. Oh, righty-o. The slope is the displacement, right? But because these are all sectioned off, if you find it, that's just going to be displacement of that portion, and displacement of that portion and that portion. But we want the total displacement, which is why we find the area under the graph for each of these and add it up. Otherwise, for the displacement of this section from 0 to 2 seconds, the displacement is 2 meters. Got it? How simple is that? I didn't understand that until now. Oh, that's why I love acting as a guide. Don't blame me, it's Alien Thought School Pro. Okay. Okay. Let's talk about this. This is the triangle, right? What do we know? Area of a triangle? Half base and side. Base 2 into 2, 4 divided by 2, 2 meters. Easy, plus 2 meters. Here, it's 8. Why is it 8? Well, 1, 2, 3, 4. 4 into 2 is 8. What's this? 2 into 2 is 4. And what's this? Same thing. 2 into 2 is 4. Divided by 2 is 2. And when you add everything up to get the total displacement, 8 plus 2 is 10. Plus 4 is 14. Plus 2 is 16. It's plus 16 meters. You need the sign because displacement is directions, right? You want to give them the directions too. So it's plus 16. Okay. And what's the average velocity? Well, the average velocity is the total displacement over the total time. The total time we know here is 8 seconds, right? Total displacement is 16. 16 over 8 is 2 meters per second minus 1. That's your average velocity. It's 2 meters per second minus 1. It can't be instantaneous because we do not know. But if you want instantaneous, we can chunk it off here. So you can get this 2 meters divided by 2 seconds. So it's 1 meter per second there. But then if you take it somewhere here, it's going to be different. Because what's the displacement here? 8 meters. Divided by the time, which is what? 1, 2, 3, 4. A by 2, it's 2 meters per second minus 1. See, it can't be reliable because here it's again 1. Here it's different. That's the instantaneous speed can be measured there. That's what all that matters. Okay, guys, we're actually pretty impressive. We have finished covering that. Oh, yeah. I wanted to talk. So the y-intercept here, right, in a changing velocity time graph, and even in the velocity time graph, right, the y-int is the initial velocity. So where it's starting, right? This is the initial velocity. And the slope is the acceleration. So in a velocity time graph, the slope is the acceleration. Okay? Because what's acceleration? It's the rate of change of displacement. So the slope is the acceleration. So in a velocity time graph, the slope is the acceleration. Okay? And the area under the graph is the displacement. Shit, I got that all wrong. Okay, so this slope is the acceleration. So if you find this area of the slope, right? So if you take 2 divided by 2, so rise over run, it's 1. So the acceleration is 1 meter per second there. Cool. Yeah. Okay. Now finally, let's look at acceleration time graph. And because acceleration for most of your prelims are going to be constant, but we're gonna have but it's constant. We're gonna have these straight lines. It's not gonna be all fancy. In your textbooks, they might have connected these lines, to make it like a box, make it more confusing. Let's just leave it here. It's fun this way. So, what's the area under the graph of a velocity time graph, of an acceleration time graph? It's velocity, buddy. I know it's funny. So the area under the graph for the acceleration time graph is velocity. When you add it all up, you get the total velocity. Because the area under the graph for the velocity is displacement, acceleration. Okay, that's cool, but that's velocity here. And let's take this, right? Again, you're doing the same thing. You're multiplying the boxes, you're multiplying each segment, each interval to find the velocity per interval, and then you're adding up it for the entire picture. So for the entire velocity of this one, it would be 6 plus 2 minus 4 minus 2. So that's 6 minus 6 already. That's 6 and 7. It's plus 2 meters per second. So it's plus 2 meters per second. That's the total velocity. Okay. Now that we've covered all 4 of these topics, right? Velocity time, position time, change time, acceleration time. Let's look at how they're interconnected, okay? How are they interconnected? How can you change between forms? Well, you can. You actually can. So, to convert a position time graph into a velocity time graph, right? You're going to use the slope, which is the velocity. Okay? Because when you use the slope, you find the velocity, right? Rise over run. Go rise, go run, rise. You find the velocity. Now that you know the velocity, you can go and put it on your axis, but in the same scales. So, if it's 2 seconds here, if it happened in 2 seconds, go to 2 seconds. Have the line at the 2 second mark. Got it? If it's 3 seconds, have the line at 3 seconds. That's what you do. Use the slope, and then you just sketch it here as per the time interval. Keep the time intervals the same. It makes life easier. So, and it's vice versa. From converting from velocity to position, there are 2 techniques that you can use. My favorite one is use the area under the graph technique. Because the area under the graph is a total displacement or total distance, whatever you're using. Area under the graph is total displacement. If the total displacement is 5 meters, you don't want the total displacement. You want the displacement per each sector, each interval. Yeah? AB, that interval. So, what's the area under the graph here? The area under the graph for this interval until 3 seconds is 3 meters. So, you graph your thing, and from, it's starting at 1, right? From 1, it starts at 0. So, for the first 3 seconds, 1, 2, 3, it's going to be 3 meters. So, go up 3 meters. Then, what about this? It's plus 4 meters for the next 2 seconds. So, it's plus 4, so it's going to go steeper. Then, we get a stagnant line for around 1 seconds. 1, 2, 3. The 3 seconds is a stagnant line like that. And then, if we go down, -2 for 2 seconds. -2. So that's how your graph, position time graph would have looked for that. So that's all you do. You find the area under there, you match the displacement to the time, and sort it. Oh, I've sorted that. Now let's look at difference where like changing from the velocity time to acceleration, but this time it's changing velocity graph. Yeah. Here, right? Here it's important. You know how the slope gives, both of them you're going to be using the slope and the area under the graph. Okay? The slope here, what does it give you in a changing velocity graph? It gives you the acceleration. Yeah, buddy. Yeah. The slope under the velocity time graph, changing velocity one, gives you the acceleration. See? So you use that acceleration here. So find the slope here, which is 2, 2, 1. 1. So the acceleration for the first 2 seconds is 1. So go first 2 seconds, acceleration would be at 1. Draw like that. That's what you do. Simple. Go ahead like that. And to convert from acceleration time to velocity time, well, you're going to use the area under the graph, because you know the area under the graph is velocity, which is what is here. That's how they're interconnected, alright? So velocity here, it's 6 meters per second. It's 6 meters per second. So 6 meters per second for the first 3 seconds, right? That's the velocity. So what's the velocity? Well, the velocity is 6 meters per second here. It's area under the graph. So for the first 3 seconds, it's going at 6 meters per second. So for the first 1, 2, 3 seconds, you're going all the way up to 6 meters per second. That's how it's going to look. You're going there. All good. So that's how you can use and interchangeably interchange the graphs. If you want to take a screenshot, now's the time. Go there. Go there. Thank you for watching, guys. I'll catch you in the next video where I go through, let me see. I'll go through the proofs. Okay? What's the next one? It'll be fun.